So, now we are going to discuss about one of my favorite topics, relativistic effects in chemistry. Without relativity, we know that gold is yellow and it is quite popular, expensive. Presence of gold, if you have gold, you are considered to be a wealthy person. The why we humans value gold so much, because of two reasons. Forget about the monetary value it has. One thing is that because gold is a quite inert metal and it colors bright yellow. So, one good thing is that it is a quite inert metal. So, it does not get corroded very easily even with the environmental effect. Second thing is that the gold in the bulk form is not very reactive. So, even if you wear it does not interact so much with our tissues, our skin. So, it is generally safe to wear. That is why gold is so valuable. On the other hand, mercury, we know it's a gray color liquid. Those who have seen that old fashioned thermometers, you have seen, or a barometer, you have seen how the mercury looks like. It's liquid, one of the very few metals to be liquid. Now, if you do not have relativity, the gold would have colored like a silver. Make it more valuable, less valuable, I don't know. Whereas mercury would have been solid. Because of the relativity, gold becomes and the yellow color solid and mercury becomes a grayish silverish liquid. So, relativity actually can play a major role in the properties, in the look, in the color of chemical compounds, and unusual behavior. Generally, this heavy element shows an unusual behavior what you consider from extrapolating it from its lighter counterpart. For example, you generally think that as I go down the periodic table, if you think of the hydride, you think that the bond length will increase. The reason is that more number of shells are getting introduced, that is why the atomic radii should expand. What happens on the case of gold, although it has an unpaired electron at the s electron at the last shell, because of the relativistic contraction, the atomic radius actually reduces. So, gold hydride actually has a smaller bond length than a silver hydride. So, that is an anomaly. And not only for the s electron, what happens is that in the case of the gold hydride, the d orbitals, although the s orbitals get contracted, the d orbitals actually get destabilized with respect to. So, if I think of these are my non-relativistic values, with respect to that the d orbitals will get destabilized and the d orbital of course will get splitted because of the presence of the relativistic effect. Same thing will be observable for silver, but generally the magnitude is much smaller. So, relativistic, so these are the relativistic orbital energies of gold hydride and silver hydride. So, the presence of relativity can heavily govern the properties of atoms and molecules which contains heavy element. And this anomalous behavior cannot be explained using standard non-relativistic quantum chemistry, that is by using standard Schrodinger picture. Now, in the relativistic quantum chemistry, what you are supposed to use is what is called a Dirac equation. This is how the Dirac equation looks like, where this V is the nuclear kinetic energy, P is the momentum operator, and alpha and beta are the Dirac matrices. So, these sigmas are Pauli spin matrices. Now, because this Hamiltonian contains the spin matrices, the spin comes inbuilt in the Dirac equation. So, its solution of one electron Dirac equations are called spinor instead of orbitals. Why they are called spinor? That it actually has an inbuilt spin part. Whereas, in the case of non-relativistic picture, the spin is actually introduced ad hoc by hand, just to make sure that I am dealing with fermion. So, it need to follow the antisymmetric properties of fermion. So, use of spin is an hand waving argument in non-relativistic. You cannot justify in Schrodinger equation because Schrodinger equation does not contain any spin dependent term. Whereas, in this case, in the case of Dirac equation, the spin is inbuilt in the Hamiltonian. Problem is that because of this, in the case of spinor, you cannot separate out the spatial and the spin part. There is no distinction. In the case of non-relativistic picture, the wave function was written as a product of the spatial and the spin part. This kind of distinction you cannot do in the case of Dirac equation. Now, if I solve it relativistic many body theory, you will have a 1 electron part and 2 electron part, like you see in the non-relativistic picture. So, the 1 electron part contains the scalar relativity, 1 electron spin orbit coupling, and the 2 electron part will contains the 2 electron spin orbit coupling, spin other orbit coupling, retardation effect, like this it will go on. Now, the wave function, the difference is that wave function you can still write as an determinant, because you want to make sure that where wave function contains the antisymmetric nature originally, but now each of this psi 1, what used to be an 1 orbital wave function, or chi in our case, actually contains now 4 wave function. And because it contains 4 wave function, they have a larger dimension because each of them is 4 times. And second thing is that because spin is inbuilt inside the Hamiltonian, now your wave function can be complex. So, if now you need to store complex number, remember if it needs 8 bit to store a real number, it will take at least 16 bit to store a complex number. Third thing is that you need to uncontract. So, to do actual relativistic calculation, 4 component relativistic calculation, you need to uncontract your basis. We have talked about the Slater functions as a linear combination of contracted Gaussian, but here what will happen, each Slater function is represented by more than one Gaussian, but here what will happen is that each Slater function will be represented by only one Gaussian. So, you need to take a huge number of Slater functions, and that means, which is essentially means uncontracting the basis. So, you are dealing with a large basis set, your dimension is large because you are dealing with now 4 times of whatever you have in the non-relativistic picture, and you need to store, each of them can be complex numbers. So, your computation cost can be very heavy. So, to do 4 component the so called Dirac-Coulomb Hamiltonian, although they can give you very accurate answer, it is very expensive and generally people do not use it beyond diatomic molecule, except some recent development which shows that it can be used for chemical application. Now, how you can reduce the computation cost? If you look what this 4 component picture looks like, this 4 component picture actually has 2 components. One is large component and the second one is a small component. So, this basically describes the electronic and the positronic solution, where the large component describes the electronic solution and the small component describes the positronic solution. So, if you look at the structure of the 4 component Dirac Hamiltonian, you can separate out the large and the small component. But before doing that, let us see one thing. So, you can see that my the spin dependent terms is in my off diagonal block, whereas the spin independent terms are contained in the diagonal block. That means, I can separate out the spin dependent and the spin free part. This is a modified way of writing the Dirac Hamiltonian, where I have a spin free part and spin dependent part. This is still, there is no approximation, it is still the full Hamiltonian. Now, the modified 1 electron Dirac Hamiltonian can be the way we have separated spin free and spin dependent. Now, I neglect the spin dependent part. So, I am just working with the spin free. So, there are 2 steps. First, I am separating out the spin free and spin dependent, there is no approximation in that. In the second step, I am just taking the spin free part and doing an FW transformation. It decouples the large and the small component. So, what I can now do is that I can only work with the large component part of the spin free Hamiltonian, and this so this L matrix is actually what it do the transformation between the separates out the small and the large component, and L is defined. So, NES is normalized elimination of the small component, and this 2 electron integrals is treated as a non-relativistic integral, because that part I have anyway neglected. Of course, you miss what is called the picture change error, and this approach is known as spin free X2C, and this is comparatively less computational costly than 4 component Dirac Hamiltonian. First of all, you have came to back to a 2 component picture, so your number of variable has reduced. The second thing is that I have separated out the spin free and the spin dependent. So, I am only working with the spin free part, and that is almost, you can actually solve it using a restricted Hartree-Fock picture. Problem, I do not have any idea about the spin orbit coupling in this case. So, for any properties which is depends upon the spin orbit coupling, if you want to do excited state spectroscopy, this may not give you, this will not give you the splitting, but where the cost is dominated by the scalar relativity, this is actually a very good approximation. And this is what we have talked about the spin free X2C. So, the Zora, which is zeroth order regularized approximation, and DKH, which is Douglas Cole Hayes Hamiltonian, they follow very similar philosophy, and they give you very similar answer for most of the properties. So, all these are scalar relativistic Hamiltonian, and to see where it is important, let us try to calculate the bond length of mercury. The experimental bond length is 3.69, and if you want to see how much is the relativistic bond length looks like, now let us see how the non-relativistic bond length for the mercury atoms looks like. So, let me open this one. So, I have used PB0 D4, there is no dispersion correction actually, but still I have used it, and I have used the X2C TZVP all. So, this is an all electron basis set, and we will see that when we go down this one. So, the number of electrons, if you see, it is 160, mercury has 80 atoms, and if you come down, the optimized geometry, the final bond length value is 2.6045, the experimental value is 3 points. So, it is 1 angstrom error it is introduced by the inclusion of by not including relativistic effect. Now, let us see how the inclusion of relativistic effects looks like. So, I can do the same calculation using Zora and use the SARC Zora TZVP basis set and SARC/J opt. And let me make the geometry 0, 1, HC 0.0, let make it 3.60 because I already know the experimental value. So, let take this liberty to make it little fast. Hg2 Zora. So, it says the 0th order regular approximation. So, the calculation is done, it took around 12 minutes. Now, if you see the geometry here, is the final bond length is 3.5731, and if I see the experiment, this was 3.69. So, the bond length agreement is pretty good, and if you see the non-relativistic values, this was a non-relativistic calculation. This is an X2C TZVP all basis set. Remember, this is all electron basis set. So, the final optimized geometry was 2.60. So, the error drastically reduces on inclusion of the relativistic effect. So, for heavier element, it is an advisable thing to include the relativistic effect. So, these are proper scalar relativistic correction to the Hamiltonian. Now, you can get a part of the relativistic effect by using effective core potential. So, just think what relativistic effect essentially means. It is the screening of the nuclear charge by the electron, which is mostly gets into the relativistic effect, and effective core potential can mimic that behavior to a big extent. So, at least the scalar relativistic part can be mimicked very well by ECPs, although these days there are ECPs available which can take care of the spin orbit coupling also. So, ECP is a very useful thing, and the advantage is that it reduces the computation cost because it removes the core electron by this potential, which is generally very easy to calculate. So, now if I try the same job, the Hg2 Zora.inp, if I save it as Hg2 ECP.inp, and of course, I will remove these options and just use a def2 TZVP basis set. So, you can see that the calculations are quite faster than what we were seeing with Zora. So, just take 1 minute 28 second. First check the bond length is 3.64. So, if I go to the experimental value, they actually give a very good agreement. It is even better than the Sark Zora because remember how much we have got in the Sark Zora. Sark Zora we have got 3.57 and the ECP one we are getting 3.64. So, actually if I compare to the experimental value of 3.69, the ECP actually looks even better, but that is not the point, that is a coincidence. There will be cases where Zora actually gives you much better values than the ECPs, but the point is that ECP actually gives you pretty good agreement with the experiment, so it can take care of the relativistic effect very well. Now, question is that why it is so fast? So, now if I go through the output file more carefully, so remember the Mercury structure, it has 80 electron. Now, among these 80 electrons, it's actually what it is doing is that it is replacing among them it's 60 core electrons, it's actually replacing it out. So, if you see the number of basis function, it's actually quite less, and this is the full atomic configuration. 1s to 2s to 2p6, 3s to 3p6, 4s to 3d10, 4p6, 5s to 4d10, 5p6, 6s2. Now you see my number of occupied electron is only 20. If I go back to the Zora example, it's 80. Remember, we are when I say 20, it says only 20, not 20 electron, it's 20 occupied orbital, so it's total 40 electron, and in this case it is 160 electron. So 80 electrons are total frozen. So 40 electron from each of the core is actually dropped away, and that actually gives you a lot of computational saving, and so this reduces the computation cost, also take care of the relativistic effect with a very little additional overhead. So using ECPs is generally very important when you are dealing with the heavier elements. And the advantage of using this DEF kind of a basis set, the turbo-mole Karlsruhe kind of basis set, is that for this basis set for heavier elements you always uses ECP, that is by default the construction of the basis set. So generally it is very safe if you are using if you are dealing with transition metal energy properties frequencies. Generally it is very safe to actually work with this Karlsruhe kind of basis set. Of course, in this discussion about relativistic effects, we have restricted our attention only to the scalar relativistic part. There is a spin orbit coupling part which is actually important, and you can evoke it by do SOC true. You can use it for TDDFT, CAS-SCF, MRCI, ROSIS, and there are cases where the spin orbit coupling can have a large effect, but generally for geometry and frequencies the effect of spin orbit coupling is generally minimal. So most of the cases it is safer to work with the scalar relativistic effect. If you want to know how to include the spin orbit coupling effect in your calculation, you can look into the manual. There are a lot of details provided there. So in this lecture you have came to know about the relativistic effect, how to include them in ORCA, and what effect it actually has on the calculated energy and properties.